Good morning or good afternoon. I'm Mr. Tong Ren from the French Atomic Energy Commission, CEA. Today I will present our recent work about the microstructure-informed modeling of the fracture toughness of alloys representing macro-segregated zones of heavy forging. This is a cooperative research program supported by CEA, Electricity of France, and Framatome. As you know, in power plants, pressure vessels are made by large forging parts. Firstly, a large size ingot is manufactured by melted metal and then formed by pressure, as shown in these figures. As the solidification of the ingot starts from the outer walls, the chemical composition is not homogeneous. Macro-segregation occurs due to long solidification time in such kind of large-size ingots, where a segregated zone, for example shown here in red, in the actual zone of the ingot cannot be easily removed by a piercing operation. This segregation event will modify the local chemical composition and eventually the mechanical properties like fracture toughness. To study the effect of segregation level on fracture toughness, three model alloys chemically representative of the carbon content encountered in the segregated zone are made and studied by Framatome. Their carbon content were respectively 0.19, 0.29%, 0.38%. Fracture toughness measurements with compact tension specimens were performed for these three materials in the low to medium portion of the brittle to ductile transition zone. As you can see from this figure, the fracture toughness obtained at each temperature are plotted. We can see considerable scatter. The green points are those for 0.19% carbon, for example. The corresponding master curves are also presented in this figure. The brittle ductile transition for the material with lower carbon content happens at a lower temperature compared with the other two materials with higher carbon content. The transition curve for the material with 0.29% carbon and the material with 0.38% carbon are quite close if we compare their master curve. Higher carbon segregation level could push the ductile to brittle transition to happen at higher temperatures. The fracture surface of these compact tension specimens were also analyzed with SEM. It can be confirmed that the main fracture mechanism is transgranular cleavage. We can also observe a mesostructure composed of micro dimples and small cleavage facets. For the two model alloys with higher carbon content, the fracture initiation site is found close to the boundary between this mesostructure and the normal cleavage facets. In addition, this mesostructure is regularly found in all of the three materials. Here in this slide, we can see the micro-segregated zones in these three model alloys. The dark zone is a heavily segregated area, which also has higher indentation hardness, so we also call it hard zone. The surface ratio of segregated zone increase with carbon content. For example, for the 0.19% carbon, only 4% of the surface is hard zone. However, for the 0.39% carbon material, it has 22% of hard zone. The distribution of carbide size in the heavily segregated zone and in the lightly segregated zone are analyzed separately for each material based on binarized microscopic image and fitted with a WEIBULL distribution as shown here. This is a binarized image for each material, and in the softer zone these three images, and in the hard zone for these three images, and this is the distribution curve. For the current study, we made the hypothesis that the cleavage fracture could initiate from any carbide in these materials, so the distribution of carbide size in each material is obtained by mixing the distribution in the softer zone and in the hard zone according to their surface ratio as presented by this function. And finally, we get a single distribution for each material. We can say for the 0.38% material, we have more large size carbides, and for the 0.19% material, we have less large sized carbides. To obtain the mechanical properties of these materials, tensile tests are performed for each model alloy. In this table, we can see the master curve reference temperature for each alloy. We have chosen 3 temperatures around their reference temperature for each case, so that the compact tension specimen toughness test can be simulated based on these material parameters identified by tensile test at the same temperature. These tensile tests were performed in an environmental chamber at low temperature combined with cameras. As you can see, speckle patterns are applied on these specimens. Through image correlation, we could obtain the stress-strain relation before netting. After netting, the stress-strain relation is obtained by Bridgman correction. The measurement of saturation reduction as the profile in the netted zone is analyzed by a Python image analysis program. Here is obtained tensile curves and the yield strengths at each tested temperature. We can see that the yield strengths increase with carbon content. Here, this image shows the evolution of yield strengths for each material. The elastoplastic behavior of these materials is described by a two-term isotropic hardening equation. The first term deals with the hardening behavior at small deformations, and the second term is used for large deformation. Each parameter is fitted with a monotonic function as shown in this image. For example, for the R0 denotes the yield strength, and the B1 in the first term and Q1 in the first term, and Q2 and B2 are taken constant in the current identification. I will give you a brief introduction to the microstructure-informed brittle fracture local approach model, the MIBF model, which is formulated in the post-processing. The main features of this model are its ability to involve both the effect of microstructures such as carbides, carbide size, or some other small inclusions, and the heterogeneous nature of local stress due to crystal disorientation or strain incompatibilities are also involved in this model. As shown on this slide, this model is formulated at 3 different scales. Firstly, the Benedict packet, which is a basic microstructure in this material. We can find some carbides in it, as shown here. The carbide cracking is controlled by the Griffiths critical stress, where R is the radius of carbide. The elementary volume level is the intermediate scale in the current model, which corresponds to a volume element in the finite element model. Each elementary volume V0 is subjected to a stress field for applied load, applied global load on the specimen, and inside each packet we have a different stress field. Here the stress distribution we can find in each packet is obtained by calculations of polycrystalline aggregates. So, the failure probability of a carbide with size R in an elementary volume is a probability to find a stress higher than its critical stress in the V0 in the elementary volume as presented in this equation. The failure probability of any carbide is then expressed here. The carbide size distribution is involved as a weight function. With a weight is a linked theory inside the V0, the failure probability of an elementary volume can be obtained by this function. Finally, we apply again the second time the weight is a linked theory at specimen level. We can obtain the global failure probability. The finite element simulation in the current work are performed on a quarter of a side-grooved CT specimen. Firstly, the global stress strain curves are validated as shown in this slide. We can say the comparison between experimental curve and simulated curves for each material for 3 temperatures around their reference temperature. For example, for 0.38% material, we have a comparison at minus 50 degree until minus 90 degree. Their reference temperature is minus 75 degree. And similarly for other 2 materials, we obtained a very good match between simulated curves and experimental ones. The fracture toughness predictions by the current MIBF model are shown on this slide. Firstly, due to insufficient number of experiments at each temperature, the surface energy parameter is not calibrated in a traditional way with a probability toughness curve. Here the model is adjusted based on the medium value of fracture toughness. For example, you can see here it's a middle point here at each temperature. And we selected the temperatures around the corresponding reference temperature for each material for calibration. For example, for the 0.38% material, we selected this point. Its reference temperature is minus 75 degree, just beside here. And similarly, for the 0.29, we have 3 points to calibrate our model, especially the gamma F. And for the 0.19%, the reference temperature is at minus 123. It's here. So the 3 data points here used for calibration is at minus 150 degree, minus 130, and minus 110 degree. These points are shown on red points on these 3 figures. Results. We can say the results showed that the MIBF model gives a good description of the scatter of experimental toughness values. The scattered fracture toughness data points can generally be covered between the 1% and 99% line of the MIBF model. The reference temperature is also in agreement with the experiments. To sum up, we have studied the 3 model alloys with different carbon contents, which are representative of those of the segregated zones encountered in large size ingot for nuclear applications. And carbide size distributions have been analyzed in these 3 model alloys and introduced in the MIBF model. For simulations, elastic plastic constitutive parameters were identified for each material based on the true stress strain curve obtained by mechanical testing combined with image analysis. and finite element simulations were conducted on CT specimens. The MIBF model was applied, combining experimentally determined carbide size distribution for each material to assess the probability fracture toughness of these materials at different temperatures. Results show that the MIBF model gives good distribution. Only compared to a Marini model, only one parameter needs to be adjusted for the current MIBF model. That's the surface energy gamma F, and the identified value of which are very close to that of ferrite, which means it has a physical meaning. And the increase, however, we also observed the increase of gamma F with carbon content to get a better prediction. So that means possibly the increase of gamma F is related to other mechanisms like microstructure evolution. Finally, thank you for your attention.